Hi, I am Miss Kea. I am a PhD student at Professor Kitek Lim's laboratory at the Department of Biosystems Engineering at Kangwon National University in South Korea. On behalf of all the co-authors of this work, I am about to introduce you to our paper titled Tempo-Cellulose Nanocrystal Capped Gold Nanoparticles for the Colorimetric Detection of Pathogenic DNA. Gold nanoparticle-based colorimetric biosensors have emerged as a robust diagnostic toolkit in medicine, mainly by exploiting their unique spectral properties upon particle dispersion or aggregation. It is well known that well-dispersed gold nanoparticle solution appear red in color, while a blue color is observed upon particle aggregation, which is greatly controlled by the capping agent used during AUNP synthesis. Carbohydrate-capped gold nanoparticles have been synthesized for the development of biocompatible nanobiosensors. However, the capping efficiency of nanocrystals of polysaccharide macroanalog are yet to be explored as they possess superior characteristics. In this regard, we synthesized and evaluated the efficiency of Temp-CNC as a capping agent of gold nanoparticles and further use them for the colorimetric detection of pathogenic DNA. Tempo-CNC capped gold nanoparticles are hereafter referred to as TC-AUNPs. In our experiment, the successful synthesis of TC-AUNPs was confirmed by the spectral absorbance at 520 nanometer, in contrast to the Tempo-CNC solution alone. The transmission electron microscopic images as well as the atomic force microscopic images of the synthesized AUNPs revealed the formation of around 30 nanometer particle. Apart from this, the enhancement in surface charge, hydrodynamic radius, and polydispersity index further confirmed the attachment of CNCs around the AUNPs. This slide shows the salt-induced aggregation behavior of TC-AUNPs in the presence or absence of single-stranded DNA molecules. Figure A is the UV visible spectra of the synthesized TC-AUNP in the presence of increasing NaCl concentration. The pure TC-AUNPs exhibited an absorption peak at 520 nanometer, which shifted towards a higher wavelength with an increase in the concentration of NaCl solution in the media. This redshift was due to the increase in the electronic conjugation between the nanoparticles, leading to the aggregation of the TC-AUNPs. No significant color change was observed up to 5 millimole NaCl, indicating this as the stability limit. A change in color from red to blue was observed in the media at a NaCl concentration greater than 5 millimole as a result of the salt-induced AUNP aggregation. Figure B depicts the changes in the ratio of absorbance at 620 and 520 nanometer, which are the characteristic absorbance of aggregated and dispersed AUNPs. As seen, the presence of ssDNA prevented the visible color change from red to blue, indicating a lower aggregation tendency of TC-AUNP in the presence of single-stranded DNA probe. Figure C indicates that an increase in the single-stranded DNA concentration from 0.25 picomole to 1 picomole further stabilized the TC-AUNPs. Next, we hybridized the ssDNA probe of methicillin-resistant Staphylococcus aureus with its complementary DNA, here referred to as target DNA, and a non-complementary DNA, here referred to as non-target DNA. The aggregation behavior of TC-AUNPs in the presence of hybridized non-target and target MRSA DNA was analyzed in the presence of varying concentration of salt. We found that at 8 millimolar NaCl and 20 femtomole of DNA, a visible color change from red to blue occurred in the presence of target DNA, as indicated by the photographs and the spectral readings. The agglomeration behavior of the ssDNA incorporated TC-AUNPs with or without target DNA in the presence of 8 millimole NaCl solution was evaluated by the ultra-high resolution TEM images. The non-target media showed the well-dispersed nature of the TC-AUNPs. However, Agglomeration of the TCAUNPs was observed in the target media. The TEM images clearly show the dispersed and agglomerated TCAUNP in the non-target and target media, causing color change respectively. This result indicated that NaCl destabilized the TCAUNP in the presence of double-stranded DNA, while the single-stranded DNA stabilized the AUNPs. Based on our results, we proposed a schematic model for the interaction mechanism between the TCAUNPs and DNA under ionic conditions. The destabilization of the synthesized TCAUNPs occurred in the presence of NaCl. The salt-induced aggregation of TCAUNPs was prevented by single-stranded DNA in a dose-dependent manner. However, no shielding effect was observed in the presence of double-stranded DNA, causing the aggregation of TCAUNPs. This difference indicates the effect of DNA conformation as a controlling factor in the colorimetric changes of TCAUNPs. In case of unhybridized single-stranded DNA, it is believed that the negatively charged phosphate groups of DNA are distanced from the TCAUNPs by the electrostatic repulsion between the negatively charged CNCs and phosphates, while the nitrogen bases are oriented towards the charged CNCs through attraction, leading to the formation of a protective DNA layer. This layer acts as a barrier for NaCl and prevents the destabilization of TCAUNPs. In the case of double-stranded DNA, which is the target DNA, all nitrogen bases are bound to their respective units. Therefore, no electrostatic attraction occurred between the nitrogen bases of the double-stranded DNA and charged CNCs, which restricted the formation of DNA protective layer around the TCAUNPs, and NaCl easily destabilized it, leading to agglomeration and consequently the color change. We conclude that a homogeneous and stable solution of AUNPs was obtained in the presence of carboxylated functionalized CNCs. The stability of the synthesized AUNPs increased in the presence of single-stranded DNA probe. A change in color from red to blue was observed in the presence of double-stranded target DNA. Our approach provides an eco-friendly, cost-effective, biocompatible, and rapid detection system based on the surface charge densities of the interacting particles. And we believe that the developed material shows great potential for its application as a biosensor for the colorimetric detection of pathogenic DNA and warrants further research in this direction. This research was supported by the Basic Science Research Program through the National Research Foundation of Korea, funded by the Ministry of Education. We would like to thank the Korea Basic Science Institute Chuncheon Center for providing us the TEM facility, and the Central Laboratory of Kangwon National University for providing us the AFM facility. And last but not the least, we would like to thank you for your interest in our research.